A statistical hypothesis is a hypothesis that is testable on the basis of observing a process that is modeled via a set of random variables. A statistical hypothesis test is a method of statistical inference. Commonly, two statistical data sets are compared, or a data set obtained by sampling is compared against a synthetic data set from an idealized model. A hypothesis is proposed for the statistical relationship between the two data sets, and this is compared as an alternative to an idealized null hypothesis that proposes no relationship between two data sets. The comparison is deemed statistically significant if the relationship between the datasets would be an unlikely realization of the null hypothesis. According to a threshold probability, the significance level, hypothesis tests are used in determining what outcomes of a study would lead to a rejection of the null hypothesis for a pre-specified level of significance. The process of distinguishing between the null hypothesis and the alternative hypothesis is aided by identifying two conceptual types of errors, and by specifying parametric limits on e.g., how much type 1 error will be permitted. An alternative framework for statistical hypothesis testing is to specify a set of statistical models, one for each candidate hypothesis, and then use model selection techniques to choose the most appropriate model. The most common selection techniques are based on either archaic information criterion or Bayes factor. Statistical hypothesis testing is sometimes called confirmatory data analysis. It can be contrasted with exploratory data analysis, which may not have pre-specified hypotheses. Variations in subclasses. Statistical hypothesis testing is a key technique of both frequentist inference and Bayesian inference, although the two types of inference have notable differences. Statistical hypothesis tests define a procedure that controls the probability of incorrectly deciding that a default position is incorrect. The procedure is based on how likely it would be for a set of observations to occur if the null hypothesis were true. Note that this probability of making an incorrect decision is not the probability that the null hypothesis is true, nor whether any specific alternative hypothesis is true. This contrasts with other possible techniques of decision theory in which the null and alternative hypothesis are treated on a more equal basis. One naive Bayesian approach to hypothesis testing is to base decisions on the posterior probability, but this fails when comparing point and continuous hypotheses. Other approaches to decision-making, such as Bayesian decision theory, attempt to balance the consequences of incorrect decisions across all possibilities, rather than concentrating on a single null hypothesis. A number of other approaches to reaching a decision based on data are available via decision theory and optimal decisions, some of which have desirable properties. Hypothesis testing, though, is a dominant approach to data analysis in many fields of science. Extensions to the theory of hypothesis testing include the study of the power of tests, i.e., the probability of correctly rejecting the null hypothesis given that it is false. Such considerations can be used for the purpose of sample size determination prior to the collection of data. The testing process. In the statistics literature, statistical hypothesis testing plays a fundamental role. The usual line of reasoning is as follows. There is an initial research hypothesis of which the truth is unknown. The first step is to state the relevant null and alternative hypotheses. This is important as misstating the hypotheses will muddy the rest of the process. The second step is to consider the statistical assumptions being made about the sample in doing the test, for example, assumptions about the statistical independence or about the form of the distributions of the observations. This is equally important as invalid assumptions will mean that the results of the test are invalid. Decide which test is appropriate, and state the relevant test statistic T. Derive the distribution of the test statistic under the null hypothesis from the assumptions. In standard cases this will be a well-known result. For example, the test statistic might follow a student's t-distribution or a normal distribution. Select a significance level, a probability threshold below which the null hypothesis will be rejected. Common values are 5% and 1%. The distribution of the test statistic under the null hypothesis partitions the possible values of t into those for which the null hypothesis is rejected, the so-called critical region, and those for which it is not. The probability of the critical region is alpha. Compute from the observations the observed value TOBS of the test statistic t. Decide to either reject the null hypothesis in favor of the alternative or not reject it. The decision rule is to reject the null hypothesis H0 if the observed value TOBS is in the critical region, and to accept or fail to reject the hypothesis otherwise. An alternative process is commonly used. Compute from the observations the observed value TOBS of the test statistic t. Calculate the p-value. This is the probability, under the null hypothesis, of sampling a test statistic at least as extreme as that which was observed. Reject the null hypothesis, in favor of the alternative hypothesis, if and only if the p-value is less than the significance level threshold. The two processes are equivalent. The former process was advantageous in the past when only tables of test statistics at common probability thresholds were available. It allowed a decision to be made without the calculation of a probability. It was adequate for classwork and for operational use, but it was deficient for reporting results. The latter process relied on extensive tables or on computational support not always available. The explicit calculation of a probability is useful for reporting. The calculations are now trivially performed with appropriate software. The difference in the two processes applied to the radioactive suitcase example. The Geiger counter reading is 10. The limit is 9. Check the suitcase. The Geiger counter reading is high. 97% of safe suitcases have lower readings. The limit is 95%. Check the suitcase. The former report is adequate. The latter gives a more detailed explanation of the data and the reason why the suitcase is being checked. It is important to note the difference between accepting the null hypothesis and simply failing to reject it. The fail to reject terminology highlights the fact that the null hypothesis is assumed to be true from the start of the test. If there is a lack of evidence against it, it simply continues to be assumed true. The phrase, "accept the null hypothesis," may suggest it has been proved simply because it has not been disproved. A logical fallacy known as the argument from ignorance. Unless a test with particularly high power is used, the idea of accepting the null hypothesis may be dangerous. Nonetheless, the terminology is prevalent throughout statistics, where its meaning is well understood. The processes described here are perfectly adequate for computation. They seriously neglect the design of experiments considerations. It is particularly critical that appropriate sample sizes be estimated before conducting the experiment. The phrase, "test of significance," was coined by statistician Ronald Fisher. Interpretation: if the p-value is less than the required significance level, then we say the null hypothesis is rejected at the given level of significance. Rejection of the null hypothesis is a conclusion. This is like a guilty verdict in a criminal trial. The evidence is sufficient to reject innocence, thus proving guilt. We might accept the alternative hypothesis. If the p-value is not less than the required significance level, then the test has no result. The evidence is insufficient to support a conclusion. The researcher typically gives extra consideration to those cases where the p-value is close to the significance level. In the lady tasting tea example, Fisher required the lady to properly categorize all of the cups of tea to justify the conclusion that the result was unlikely to result from chance. He defined the critical region as that case alone. The region was defined by a probability of less than 5%. Whether rejection of the null hypothesis truly justifies acceptance of the research hypothesis depends on the structure of the hypotheses. Rejecting the hypothesis that a large paw print originated from a bear does not immediately prove the existence of Bigfoot. Hypothesis testing emphasizes the rejection, which is based on a probability, rather than the acceptance, which requires extra steps of logic. The probability of rejecting the null hypothesis is a function of 5 factors. Whether the test is one- or two-tailed, the level of significance, the standard deviation, the amount of deviation from the null hypothesis, and the number of observations. These factors are a source of criticism. Factors under the control of the experimenter. Analysts give the results an appearance of subjectivity. Use and importance. Statistics are helpful in analyzing most collections of data. This is equally true of hypothesis testing, which can justify conclusions even when no scientific theory exists. In the lady tasting tea example, it was obvious that no difference existed between the data contradicted the obvious. Real-world applications of hypothesis testing include testing whether more men than women suffer from nightmares, establishing authorship of documents, evaluating the effect of the full moon on behavior, determining the range at which a bat can detect an insect by echo, deciding whether hospital carpeting results in more infections, selecting the best means to stop smoking, checking whether bumper stickers reflect car owner behavior, testing the claims of handwriting analysts. Statistical hypothesis testing plays an important role in the whole of statistics and in statistical inference. For example, Lehman in a review of the fundamental paper by Neyman and Pearson says, nevertheless, despite their shortcomings, the new paradigm formulated in the 1933 paper, and the many developments carried out within its framework continue to play a central role in both the theory and practice of statistics and can be expected to do so in the foreseeable future. Significance testing has been the favored statistical tool in some experimental social sciences. Other fields have favored the estimation of parameters. Significance testing is used as a substitute for the traditional comparison of predicted value and experimental result at the core of the scientific method. When theory is only capable of predicting the sign of a relationship, a directional hypothesis test can be configured so that only a statistically significant result supports theory. This form of theory appraisal is the most heavily criticized application of hypothesis testing. Cautions: if the government required statistical procedures to carry warning labels like those on drugs, most inference methods would have long labels indeed. This caution applies to hypothesis tests and alternatives to them. The successful hypothesis test is associated with a probability and a type 1 error rate. The conclusion might be wrong. The conclusion of the test is only as solid as the sample upon which it is based. The design of the experiment is critical. A number of unexpected effects have been observed, including the clever Hans effect. A horse appeared to be capable of doing simple arithmetic. The Hawthorne effect. Industrial workers were more productive in better illumination, and most productive in worse. The placebo effect. Pills with no medically active ingredients were remarkably effective. A statistical analysis of misleading data produces misleading conclusions. The issue of data quality can be more subtle. In forecasting, for example, there is no agreement on a measure of forecast accuracy. In the absence of a consensus measurement, no decision based on measurements will be without controversy. The book How to Lie with Statistics is the most popular book on statistics ever published. It does not much consider hypothesis testing, but its cautions are applicable, including many claims are made on the basis of samples too small to convince. If a report does not mention sample size, be doubtful. Hypothesis testing acts as a filter of statistical conclusions. Only those results meeting a probability threshold are publishable. Economics also acts as a publication filter. Only those results favorable to the author and funding source may be submitted for publication. The impact of filtering on publication is termed publication bias. A related problem is that of multiple testing. in which a variety of tests for a variety of possible effects are applied to a single data set and only those yielding a significant result are reported. These are often dealt with by using multiplicity correction procedures that control the family-wise error rate or the false discovery rate. Those making critical decisions based on the results of a hypothesis test are prudent to look at the details rather than the conclusion alone. In the physical sciences, most results are fully accepted only when independently confirmed. The general advice concerning statistics is figures never lie, but liars figure.